Okay, Bismillahirrahmanirrahim and Assalamualaikum warahmatullahi wabarakatuh and a very good morning to everybody. So for today we will have a training sessions with Solehin, our lab mates, regarding the molecular dockings. Okay, as we know, we cover a lot of and diverse domains in our research to make sure our quality of research and to answering some of the why factors that we do during the research. Okay, molecular docking is a kind of computational chemistry, and I hope everybody can explore that one. They have a huge potentials to explore. And for example, our Deputy Vice Chancellor, Prof. Habibah, is also a part of in silico's chemistry, which is expert in computational chemistry. So they have so many opportunity if you can master this kind of chemistry. Okay, so please pay attention to the Solehin. I think Solehin will explain about the flow for today. And if you have any questions, just ask Solehin, don't worry. So maybe in the end of the sessions, I will give some advice or my personal thought about the molecular dockings, how and why some examine, what is the question they will ask from the examiners regarding the molecular dockings. So as I explained in our groups, we have this book in our libraries. Okay, please find your time to explore the library. They have a huge and good, very good book. I spent one day there and they have a lot of books there. Okay, please spend your time there. Okay, because you pay for the servicing to enter the libraries and we buy the books and we put it there. So please use it. Okay, without further ado, now I give this authority to my co-host Solehin to explore everything. So Solehin, you may continue.
Okay, can you hear me? Okay, Assalamualaikum warahmatullahi wabarakatuh and very good morning. Good day, everyone. Okay, before we start this session, I've already mentioned to you that you need to install all of the software. Did you already install? Okay, if you already install, it's fine. It's okay. If you don't install it yet, it's okay. Later, you do it after this session. Okay. The software that we use here is CamDraw, Camera, Autodesk Vina, Discovery Studio, PyMol, and optional is OpenBabel. Okay. Before we start, I just like to introduce a brief introduction of the software that we will be used here. Is starting with the CamDraw. CamDraw is to draw the structure of chemical compound, and also to prepare the simplified molecular input line entry system or SMILES, and also to minimize the compounds. And next is we use I use CSF camera. Wait, I need to use pointer here. Okay, we see SF camera. I use this interactive visualization and analysis of molecular structure. Actually, this camera is the shortcut for us to prevent the use of command prompt in Autodoc. We use a simplified user interface. And this UCSA camera is used to prepare the chemical compound such as ligand, protein, which is a receptor, and a docking parameter, which is a grid box size and center, before starting the molecular docking experiment. And next, we use Autodoc Vina 1.2.5. There are two types of Autodoc docking software, which is we use Autodoc. There are two types of Autodoc software, which is Autodoc 4.2 and Autodoc Vina. But in this lab, we currently use Autodoc Vina due to its simplicity compared to Autodoc 4.2. This Autodoc Vina is used to predict how ligand bind to a receptor of known 3D structure, such as a protein, enzyme, or homology model. This Autodoc Vina uses a hybrid scoring function based on X-score function, and we use this software because it's faster and quicker in identifying protein ligand complexes. And next, the fourth software that we use here today is BioVia Discovery Studio. BioVia Discovery Studio is used to prepare the protein prior to molecular docking experiment, and the main function is to analyze and visualize the ligand-receptor interactions in 2D and 3D forms. And next, PyMol. Actually, PyMol not everyone use, but actually it is one of the most important software. It is used to validate the docking parameter, the docking method, by superimpose the reference co-crystal and the redox complex. This is, I will explain it later. It is quite confusing at first, but later you will understand what I mean about this superimpose. And lastly, OpenBabel. OpenBabel is the software that we use, alternate software that will be used to minimize the compound, to minimize the ligand. When using ChemDraw, we will minimize using MM2 force field. But using OpenBabel, it have like 30 of force field that you can use. But in this lab, we prefer MM2 minimization because it is widely used on small molecules and carbon compounds. Okay, next we move to the step. Okay, before simulation, it is better for all of us to find a good literature up to what we want to search. Like if you want to do diabetes, we use alpha glucosidase and alpha amylase. And if you want to use Alzheimer, you find the literature that related to Alzheimer disease that use like cholinesterase activity. And if you want to proceed with a cancer study or cytotoxic, find a paper that relevant to the cytotoxicity. Okay, during finding suitable literature, the keywords here that is widely used by researcher from most of the paper in Google Scholar or any other literature, which use the term in silico, term molecular docking, virtual screening, and molecular dynamics. This is a few of the keywords that you can use to find your specific literature. And then after find the suitable literature, you select one and you focus on methodology and finding. Okay, when you observe and read the methodology, just focus on the protein data bank ID or PDB ID. If it use the PDB and protein from PDB, or if you use the homology model, find the homology model between the citations. Maybe it will put into the citations lastly. And the protein resolution, the grid box size, the grid box center, and what type of docking software they use. And also the researcher use energy minimize or structure optimize. And then after read literature, you can compare with another literature. It means that you don't read one paper only. You need to read a few so that you can compare which method is suitable for you and which method is the latest. And then find the reasoning behind the selection of the method, such as why you choose this receptor, why is they use the grid size and center, why use only chain A and chain B, and is it active site or catalytic site, and what amino acid residue that is responsible for the inhibitory activity. This is a few reasoning that you can find inside the paper. Okay, moving on. Okay, this is a paper from our colleagues. You can see here, this is Laksani and Shira paper using 4 anti-diabetic study. Okay, we can see here, this is from the method. I just screenshot the paper, and we can see for the method, it clearly states that it used a C-terminal of human maltase glucoamylase complex with acarbose PDB-ID 3 top. Okay, this one, the PDB-ID that I mentioned to you, you need to highlight this PDB-ID 3TOP and PDB-ID 2QV4. Here, they use 2 types of proteins because they do 2 types of assay. One is alpha glucosidase, one alpha amylase. So they use two types of protein here. And The software that they use is UCSF camera. UCSF camera is the interface, and the binding energy score were calculated by Auto.Bina. It means that they use a UCSF camera in tandem with Auto.Bina. And we can see here the grid size for the alpha amylase. They use for alpha glucosidase, sorry, they use 108 angstrom, 83 angstrom, and 137 angstrom. You can highlight this one, and also 0.375 angstrom grid spacing with the grid center of negative 38A, 13A, and negative 13A. Okay, this is the interesting part lah. You need to highlight and take notes if you are doing docking for alpha amylase, alpha glucosidase, sorry. And then the second one is the alpha amylase, the green highlight one. You can see here, it said that PDB ID 2QV4 and complex with nitrite net alkabus. Just take note this one with the grid size of 61 angstrom, 107 angstrom, and 59 angstrom. Okay. And also the grid center of 20A, 46A, and 18A. Okay, finish of this one. We proceed with another paper just to give you a brief idea about how to find the literature, how to find the method that you need to highlight before you running a docking. Next, we move to the I think recent paper from Dr. Azmi, organic communications that use cytotoxicity study by the docking run using the inhibitor of nuclear factor kappa B kinase alpha or RKA, IKBA. The PDB ID is 1NF1. The user software used here is UCSF camera in tandem with Auto.Bina with the grid size of 27, 38, and 39 XYZ with 0.375 angstrom grid spacing, and the grid center along the XYZ set to negative 5.9, 81, and 59 angstrom for the docking searching purposes. And he said that the water molecules, chain A, chain B, chain C, chain D, and chain F were removed. It means that this is such a big protein. They just like a few targeted chain, which is, I think, is chain E. Since no E here, A, B, C, D, no E, F. Okay, it means they use chain E. And this box is a location where few of N terminal of IKBA residue interact with an FKB molecule. It means it have the specific reasoning where they choose this chain E and also where they choose these coordinates. Okay, at this moment, I just ask if you have any questions about how to choose the literature. Can you listen to me? Just open your mic. I have we start with the Q&A at this moment first.
Solehin,
Yeah.
I think I have one question just to project to start the sessions. Actually, they have a lot of code in PDB files when we try to access the website or PDB website. So how we can choose the exactly ones, the correct ones regarding the protein that we want to do molecular docking?
Okay, the protein that you want to do molecular docking, the correct one is you need to read first. You need to really read about, because we don't have direct interact. We call doctor, I need to think first. But on how we choose is we read the recent paper that what you call correlated to our research, and how to determine whether it's correct or not. I think you need to read, really need to read. But on how to choose it, I have no idea at this moment.
Okay. So, okay, this is the question that usually the examiner asks, the reviewer asks, how confident you are choosing the correct proteins. The second one, okay, so how we want to make sure this is, okay, for example, we are doing alpha amylase, which is these types of alpha amylase, and after that, we are doing docking with this type of this type of proteins. How we one can match these two, okay, and confident this is coming from the humans. And mimic the human system. Do you have any ideas, Solehin?
Maybe the at this moment I started. Later I find the
Okay,
answer.
okay. It's okay, it's okay. Because this is recently asking the questions. I think it's paper for Laksani last times. Okay, it's okay. Anybody who have question, please ask. This is just relax. Okay, for this is very helpful sessions. Okay.
Any questions?
Yeah, is it clear? Or we have in chat box once. Let me check.
Okay, let me check.
Oh yes, okay. Only yes. Okay, Nizam. Thank you.
Okay, maybe we can just proceed.
Please, Solehin, thank you.
Sorry, Doctor.
Please proceed. Don't worry.
Okay, before starting the simulation, we need to prepare the ligand. Actually, I will show to you step by step using the software, but I just mentioned it briefly using the slide at first. Okay, how to prepare the ligand using the ChemDraw. We draw the structure because I mentioned it to you before. We draw the structure using ChemDraw. There's actually a lot of software that can be used to draw a compound, but specifically for this lab, we use the what you call the latest method the current one we use is ChemDraw. And second, you need to visualize and minimize the structure using Chem3D, which is also inside the ChemDraw using the MM2 phosphate. Why I choose MM2 phosphate is widely used in organic compound. It's highly stable compared to another phosphate, and we just save it into 3D, save the 3D structure as a PDB format. The alternative method, if you don't want to use ChemDraw, for minimization, you can just draw the structure using ChemDraw first, and then you copy my string from ChemDraw and paste into Chimera using the build structure functions and minimize using Chimera.prep tools. But I suggest the using of .prep tools in Chimera is not really reliable because the algorithm for the minimization is not really good and not up to date. It used another phosphate, I think amber phosphate, which is not really good. And we just use MM2 phosphate here. Okay, let me start with the software. I will go directly to the software first. Okay, let's see here. I have a compound. This is the compound that I draw at first. You can use your compound. Oh, sorry. Okay, I want to share. Share this one. Yeah, okay. At first, we open the ChemDraw first. Okay, you draw whatever you want to draw. Your chemical compound, also known as ligand. In docking, we call your compound is ligand. The term of ligand and chemical compound is interchangeable. So here, I will proceed with our chemical compound. Okay, we draw our chemical compound. How to draw, you need to know. We have another workshop on how to draw, but it's okay. I assume that everyone know how to use ChemDraw at first. Okay, let's say this one for isobutyrate oxy, phenyl methyl phenyl isobutyrate. Okay, this is a 2D structure, and how to change from 2D to 3D from by using ChemDraw is we just select the option of view and Chem 3D hot link window. Okay, the Chem 3D hot link window will show the 3D structure, and then we need to minimize it. Okay, we use launch Chem 3D. Just click launch Chem 3D. And wait, because the software is quite heavy to load, but it's okay. And then after, can see Chem 3D? Wait, I need to, after you press Chem 3D, wait, Chem 3D. Okay, this is the interface of Cam3D. As you can see here, this is the interface of Cam3D. Okay, from the toolbar here, you can see the MM to minimize. The MM to minimize, you just click. Okay, let the computer do the simulation, the simulation of running the MM to minimization. You can see here it's moving. It will minimize to the lowest energy. We want they will grant a steepest gradient, and also we want the lowest energy. Okay, we wait because the performance of this minimization is up to your computer specification. If your computer specification is good, this minimization will be fast. Like mine is 11 years computer, so just wait. We do it on real time so that we will not miss anything. Okay, calculation ended. With the total energy of 19.24449, is up to you if you want to save the data or not. But for me, I will just not save it. I just want the structure. I don't want this one total energy, because if you are doing molecular dynamics, this one is the needed one. But since we are just doing docking simulation, the data here, we just simply ignore it. If you want to take it, just copy and save. Okay. Next, we want to save this minimized MM2 structure using in a PDB form. Just click File, save copy as. Okay, you prior to docking, you need to prepare one specialized folder for your docking file. Like say this one, I want to run the docking on IKBA 14. So I just save it into this one. I just make it cytotoxic docking, because this one I want to do the docking for cytotoxicity study. Okay, you make a one folder, and you just simply name your compound. Like this one is compound 3B. I just make it min. 3B minimize. I will put 3B minimize and save it in a protein data bank PDB format, and then click save. Okay, this one this one pop up, just ignore it, close, and then here we finish preparation of the ligand, minimized ligand using MM2 phosphate. Wait, I want to share the slide first. Okay, next we proceed with the preparation of receptor. Okay, receptor is interchangeable with protein, enzyme, homology model of protein. That three things are almost are the same. Receptor, protein, enzyme. Okay. Okay, how to prepare receptor? First, we download the protein data bank, the protein data crystal from protein data bank website, which is this link. And we need to find a crystal which is a very good in resolution, with the range of 1.0 angstrom to 3.0 angstrom. It means that the lower the value, the better the resolution. And then we visualize using camera or Discovery Studio. This is optional. We remove the water, heteroatom, and another things, etc., leaving only the needed protein structure, and save the protein structure as PDB format. Okay, the alternative method that we can use to find this protein data, to retrieve the protein data crystal, is you just simply copy the PDB ID and paste it into camera using the build structure function. But I will start with download the protein data bank first. Okay. Okay, this is the website of Protein Data Bank. You can just simply Google, like if you don't know, you just PDB, Protein Data Bank. Just simply click here. Okay. Since our protein of interest is the cytotoxicity study, the slide that I showed before, the IKBA, okay, I just use this protein ID 1NF1. This is really up to your research interest. Like this one, I use cytotoxic, so I use this protein 1NFI and click this one. Okay, we can see here, this is the protein structure. IKBA, I'll check again, is it good or not? Okay, we can see here the resolution is 2.7 angstrom within the certified limits, 1 to 3. But if you can find the protein which more lower than this one, it's much better. But at this moment, we use this one because it's still within the limit of 3 angstrom. So this one, 2.70 angstrom, and this the website show a lot of things here. At this moment, you can read on your own this one. If you're interested to read one by one, it's good. But if you, since we just process on docking, we just proceed to this next step, which is we download the files here, download the PDB format. Okay. Okay, the file is already downloaded. After it's already downloaded, make sure you copy the file that you download and paste it into the specialized folder. Let's go and check. Like this one and F1, this one I copy. I just put into my specialized folder, which is cytotoxicity. Paste. I name it. Okay, we got the receptor protein, and we got the 3B minimized. And then we need to proceed with the processing the protein before docking. Prior to docking, we need to process. Okay, at this step, I use camera. Okay, I need to open the camera first. Okay, stop sharing. Okay, this is the interface of camera. Like I mentioned to you before, we need to process the protein first. Because the protein that we download have a lot of such a big protein. From the literature, they said that they just want to use a chain E only. We need to remove the unwanted unwanted heteroatoms and unwanted chain. So I need to open the protein. Okay, open. Wait, I have a file here. Okay, open. Okay. This is such a clumpy protein. A lot of happenings here. But from the literature, it said that just use a chain E only. So we need to delete the one that we don't want. Okay, how to delete? We need to specific first. Okay, select, go to chain. E, the one that we don't want, the one that we want, chain E. And then go to select again. we just use invert all models. Okay, and then action, we want to delete all of this chain. Go to action, atom and bond, delete. Okay, this is the one that we want. And again, we need to delete any heteroatom that present here. You go to select, you go to change, only left here is E. You go to residue. We don't want water. So we click HOH, is water, action, delete. Okay, water is now delete. We cannot see here the water because it's really small. Okay. Okay. All are clear since it reach an E. Residue was all amino acid here. Okay, all good. And then we need to save it again. Okay, how to save it? You go to file and save PDB. Okay, you put the naming since this is 1NF1. So okay, this one I just make actually the naming is up to you, but I make it here 1NF1 prep, which is already prepared. We use for protein we use prepared. For compound we use minimize. Okay, and then just click save. Okay, and then we finish on preparation of the protein. Let's close the session. Okay, next we need to run the to prepare the box whatsoever. Okay, wait to share the slide. Okay. Okay, at this step we already finished for the preparation of receptor. We proceed with the simulation. During simulation, Salva, I can see your microphone is turning on. Can you mute your microphone? Thank you.
Yeah, it's clear for me.
Okay, for simulation, we use Chimera and Autodoc Vida. Okay, the step I've what you call well, I just summarize it here, but I will show you step by step using the software. Okay. If you want to take a picture, you can take a picture because after this is I just use software. But if you want to write it, just take a picture. Okay, we proceed with the docking. Okay, we need to open the camera, UCSF camera back, and then you open. At first, you open your protein, which is one NF1, the one that we already prepared, one NF1 prep. Open. Okay, and then go to file again. We open our ligand, which is our compound, 3B, minimize, open. We don't see the compound, but the compound stay here, very bottom, the bottom of this slide. This somehow really far from the protein, but it's okay. This doesn't affect. At least we can see the compound here, the protein is here, is okay, it's enough. You can play around. You see, okay, this is when at this view we can see it's clumping, but this view is not clumping, it's like linear. Okay, and then we proceed with the docking. Okay, the step is go to surface binding analysis and Autodoc Vina. I'll maximize this one. Okay. For output file, you need to name your output file. Use the same folder of your docking. I just make it, the name is, you need to name your docking file first. Okay, I just put 1NFI prep underscore 3B minimize. And then I put T1. Why I put T1 is trial 1. Because a docking we need to run 3 times. I put T1 here, like test 1 or trial 1. But the naming is really up to you how you name. This is like my way of how I name my compound during docking. Also, this is the way. Okay, and then just set output location. And then for receptor, need to make sure is 1NF1 prep, our protein, and ligand is our compound. That here is 3B minimize. Okay. And then since from the paper, I already have the center and size. Okay, I just put the coordinates here. Like this one is negative 5.90, 81.00, and 59.00. And the size is 27.00, 38.00, and 39.00. And then for receptor options, all true except ignore all non-standard. This is the only false. By default, all true, and this one false. Just use this. And then ligand options, also both are true. Just use the default setup. Advanced option, this one you can customize. So you can customize how you want to have how many binding mode you want, isotonic or search, and maximum energy calorie. But here I use the default one, which is 10 for binding modes. Exhaustive or search is 8, and maximum energy is 2. If your research want a really really tight on the energy difference, you can play it like 1, but 2 is okay. And then proceed with executable location. Okay, the executable location is the path that you need to put your autodoc.bina.exe that you already download, like mine. If you have download the exe file auto.bina, you need to create one folder in local DC, and you just paste the auto.bina exe file that you download before, and you just browse and just select the path, copy the path, and the software will read the auto.bina. You cannot open Bina 1.2.25e by simply clicking the exe file, but this auto.bina can only run using this one, using this auto.bina tools in Chimera. If you have questions on this later, you can ask me, but I just make it short here. Okay, everything is fine, everything is clear. You can see. Okay, the grid box covered the chain E, and also the active site that the paper said they have the catalytic site. And then we finish this one and just click OK. You can see here. Of course, we have the problem adding hydrogen, because this one, I think the protein have missed 1 hydrogen, but it's okay. The simulation can still run, and the result will not affect due to one atom only. But the result will be fine, good for the whole protein, not on this problem only. It's okay. We can proceed. Just close. But you can see here, the simulation is still running. At least it runs. It's okay. And then we can see here, you can see here the result of the docking just pop up here. Like it have 10 energy modes, like because we select 10 type of energy binding mode, so we show here 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you choose 5, it will be 5. If you choose 8, it become 8. But if you choose 10, but if the docking is not done really well, somehow it will pop up with just 5 or 2 or 3 lower than you select 10. It's okay. It's because the algorithm is quite different, and the protein, maybe your protein that you put are really complicated, and the software cannot process to give you 10 binding mode, but can provide you less than 10. But it's okay. We just proceed with the lowest one. Okay. After simulation, you can see, I need to maximize this one. Make sure that, okay. You can play around to see, out of 10 binding modes, okay, this one, the lowest one is here. You can see here. Second, here, here, here. Okay. All have 10 variables. But if you want to know which one is the most active, the active site, which one is the most active site here, you just click this one and click control. Just push the control button and highlight it one by one. It means that this compound clumped at this side and also this side. So it's okay. The active site that we choose is okay. We can proceed with analysis. Okay. I just want to elaborate on this one. This is the score. The lowest, the better. This is like negative 5.49489 RMSD lower base and RMSD upper base. This 0 mean nothing. It means that the second ligand is 16.8 different from the first ligand, the lowest ligand here. You cannot simply take this RMSD to put in your paper, because this is just rely on the first position of the docking. But later I explain in personal, because this is hard to explain using this software. But it's okay. We just proceed with this one, the lowest one. Okay. Next, after the docking simulation finish, we want to save the file. Okay, how to save the wanted file here? I just select file and save PDB. Okay. We need to put a file name again, like one NF1 prep, PB me. For me, I like to put all models in one file at first. Later, I explain why I put all models in one file. I just put it all model. One, all model. And here, you need to remember, when you save this whole file, it will have like 11 models here. But at first we just use 10 model, but since we save model relative to our protein, it will become 11. I just select all except the original one. Original one I don't want. I just want the protein and the docket and the doc ligand, which is 3B mean 1 model 1, 3B mean 3.2 model 2, up to model 10. And then save relative to model, yes, one NFI prep, and save multiple models in a single file. Just use a single file. And then click save. before we go, we finish with the simulation. Okay, at this moment, is it okay? I can see the chat said that, can you please explain more about executive location? If you do the docking, you download the file, the exe file. Say this one, I open, wait. Let's see, it's sharing. Window Explorer. Okay, if you download the exe file, like this one, it's okay. You just copy from your download folder. You create one special folder for the Vina auto.vina. You go to this PC, you go to local DC, go to program files, x86, and you just create one folder, which is auto.vina. And then you paste this one. You paste the exe file. Okay, clear at this step, clear? And then we proceed with how to execute the location. I stop sharing the Explorer. Okay, from the camera, you can open back the surface boundary analysis and auto.vina. This one, the executable location, the path, you just select the path that you create for auto.vina, like user program file x99 x86 auto.vina. Select this one. It mean executable location, the software that we put the Vina. Okay, finish. Is it clear? Ibrahim, you ask question, is it clear? Okay, and then we proceed with the next step, which is the visualization. Okay, after finish the docking simulation, we need to visualize. How to visualize? We use BioVia Discovery Studio. Okay, I just minimize this using as a camera. Okay. Wait. Okay, we open up our BioVia Discovery Studio. Wait, because it's taking slow at this moment, but it's okay. Okay. Okay, we proceed with BioVia Discovery Studio. You can see here. Okay, and then select file. We open the docket, the all model docket. Okay, open. Go to our folder of docking and select this one, the all model. And then open. Okay, we can see here the clumping of the ligand at the active site of the protein. Okay. And then we just click this one to see the multiple, the model here. Okay. From what we save using camera, we can see that it have 11 model, but bear in mind, the model 1 is the protein. The model 1 here is protein, and the model 2 is a ligand. The model 2 is the ligand in what you call it? In Discovery Studio, but it is a model 1 for the binding energy. I repeat, model 1 is for model 1 of Discovery Studio is the protein, but the model 2 of this ligand is the model 1 model 1 of the camera, the lowest binding energy one. Bear in mind, don't change because before this is 10 binding modes, but now it have 11. So just neglect this one. So is model 2 equal to 1, model 3 equal to 2, model 4 equal to 3, U minus 1, U minus 1. U minus 1, how to calculate? Okay. This one is a protein. So to view the interactions, we need to define the receptor. Okay, define receptor, this is model 1. Model 1 is the receptor. So click this model 1, it becomes the receptor. Okay, and then for the ligand, we use the lowest energy state, which is the model 1 in camera, but is model 2 in Discovery Studio. Just click this one. Okay, we can see. The other one, like 3 to 11, then you just need to untick it. Okay. You can see here the protein with the ligand, and then the one that we really want to know is the ligand interactions. Just click ligand interactions. Okay, ligand interaction, we can see it have the green dotted line, pink dotted line, purple dotted line. It's okay. And then how to see it clearly? Show 2D diagram. Click show 2D diagram. Okay. And then it pop up the one that we want to use. This is a 2D. So we can see here the BPHE77 form hydrogen bond with CO. And PHA13 form pi-pi step interaction with the benzene ring here. But it's really depend on your compound, on what and what is your receptor is. And then from this visualization, you can play around to change the display style. Like yesterday, we see that Idris used a stick or line, which is not really clear. You can customize how the atom should be shown in your 2D diagram. Like here, line. This also can, like this. Stick also can. Ball and stick also can. It's up to your preference. But for me, I prefer ball and stick. I prefer ball and stick. I can play around with the ball size, like 0.30 size. Yeah, it's clear. But if you want to use stick, make sure your stick size not really thin. This one too ball. Maybe you can use 0.20. It's up to you. You can play around. This one okay, nice. And with the residue, we just set it to ball much better. But if you want to use plate, somehow in paper they use plate, also can. This or ball, but in we use ball. You can play it around. Interaction, what you want to show, but it's okay. Just leave it there. Okay, and also you want if you want to change the font, also can change the font. But we use here Calibri. Okay. Okay, for this one, and then if you want to save this one for publication, you can use tools. This one is tools. You just go to script visualization, publication quality to ensure the graphic is nice. Okay. Actually, this is the 2D diagram, 2D conformation, and this is the 3D conformation. We just proceed with this one first, the 2D first. Okay. After you select the script visualization and publication quality, it's okay. You need to save in files, they call image file. You can just go to file and save as. Okay, model 2, all good. I think the naming is good. Model 2, I just like to bracket 1 lah. 2 is in the Discover Studio. 1 is the real model, and use the image file and save. Okay, the width and height is up to you, but if you put 10,000, it's so high, I just put 5,000 pixels. Okay, and then click OK. It will take some time to save. And then we finish on the 2D. The 2D, and we then proceed with 3D. Because some paper need 2D, some paper need 3D. But some paper also have both. It's okay. Okay, we close the 2D. Then we proceed with 3D. Okay. 3D, if you don't put the high quality, you will get a very, what you call a pixelated picture. So it's better for you to have a publication quality. And then from the 3D, we can see that there is no naming of protein here. So we need to put how to label it. Just right click and go to labels and go to add. Okay, here the item is we don't want to label. We just want to label the amino acid. And then the font, the size is really up to you design. If you want to use whatever font, up to you, and apply. Okay. Like this one, we can see that the image, the name of the residue is not really clear. Also, it's okay. And then we need to just change it. Okay, sorry. Remove first. Labels, add amino acid. Color, maybe you put red or black. Font, maybe you can increase it. And apply. Apply first before you select the whatever font that you want. But yeah, it's okay. It's okay. I think I use Arial black. Arial black. Okay. Okay. If you want to change the color to red, just red color. Okay. And then we finish this one. You can, but please, before you save this 3D form, please make sure that your graphic, the confirmation is good in beside that we can see the name of the residue, and we can see the structure of the compound. Okay, like this one, I think it's okay because we can see the interactions. But it's really up to you. If you up to your preference. I don't limit the preference like this, like what, but it's really up to you. Okay, I think this one good because we can see the protein, the amino acid residue, and also the compound. And then you go to file, it save as. Sorry. File, save as. Oh, sorry, I think it's got error here, but it's okay. Okay, all model. Save. Just put it 3D to make sure you know this is a 3D form. Same, I set it to 5,000. Okay. And then finish. We finish on visualization and also the interaction. Okay. Next, if you want to give a deeper analysis of this protein ligand complex, I will explain to you more. Okay. I just shut first. I want to see this one. I reopen my file. Okay, I repeat the step, but in fast mode. Okay. You can see here the clumping here. We just want the receptor is model 1. Our ligand with the lower state is model 2, which is 1 in camera. And then we just unclick this one of this thing. Okay, this one, the lower state one. And then go to ligand interactions. Show to diagram. And then how to change it to 3D. Just go to script, visualization, publication quality. Then labels, we add labels here. Add amino acid. Yeah. Okay. And then if you hard to find to see this interaction directly from 2D, you can also use this function here, which is this toolbar here. You just go to non-bond. Okay, you can see non-bond here. Okay, non-bond, we can see like this one. The green PHE 77. It have the hydrogen bond, which is conventional hydrogen bond. And then SIR76 have the hydrogen bond, which is carbon-hydrogen bond with distance of this one. Okay, for hydrogen bond, you need to take note on the distance. For the true bond, I call it true bond. If hydrophobic interaction, no need to really discuss about the distance. But for hydrogen bond, only hydrogen bond, the true hydrogen bond. If it's conventional hydrogen bond, you need to take the distance. You just take note the distance. Okay, finish of this one. By step by alkane. Okay, and then we finish off this one of visualization. Okay, I open to question and answer if you want to ask about the visualization. Is it clear?
Assalamualaikum.
Salamullah.
Assalamualaikum.
Salamullah. Ya.
Assalamualaikum.
Waalaikumsalam. Ya.
Yeah, I want to ask Brother Solehin about the hydrogen bonding. Sometimes we can find that we have the one with the highest energy, but there's no hydrogen bonding. So and some we can find with lower energy, but it have different hydrogen bonding. So
okay.
which one is the best? Which one is the best? Having hydrogen bonding or having the lowest energy?
For me, I prefer the one that have hydrogen bond instead of hydrogen energy, instead of lowest energy. But don't what you call the energy difference not so big like Before the one model 1 maybe don't have hydrogen bond, but model 2 or 3 have. I can select model 3.
Okay. So
We
that means
prefer
hydrogen
the
bonding.
good bond.
Okay, that means hydrogen bonding will other hydrogen is the best binding. Is the best docking.
Yeah, because it's a true bond compared to another thing. But also pi also good. But compared to hydrogen, the what you call the interaction is more preferred on hydrogen, because if got hydrogen, this is such a strong explanation there.
Oh. Okay. Thank you.
Welcome. Okay. Before that, this is the model 1, which is really good. We can see the hydrogen bond here, pi sigma and so pi stack. We can, if you want to observe another model interaction, also can. Okay, I just close this one. Okay. Click this one. The model, of course, the receptor is model 1. But the ligand now, before this model 2, we click to model 3. Okay. Okay, model 3 and ligand interactions. And then show 2D diagram. Okay. This one also good, because it have two hydrogen bond. Hydrogen bond. It's up to you how you choose, but because the energy difference is not so big, like before this, like 5.461. Okay, I open back the energy the energy table. Okay, I just minimize this one. Oh shit. You got explode or not? Wait, I need to show you. Okay. How you find the data of your docking of your you want to know the energy binding energy of your docking. You can see you open your docking folder. You go to this one, the one that have the PDBQT one, and this one, T1. This no receptor, no ligand, only .pdbqt. You click this one. Okay, you click this one, the text file, and then text file, and then it will show up here. Okay. Model 1, the binary result show the energy is negative 5.489 with all of this. You can highlight this one. But this is model 1. And then we go to model 2, 5.396. Also not really a difference in energy. So if you found that the model 2 have a good more hydrogen bond and more good in interactions, you can choose model 2 or model 3. At least you see the energy is not really different. If the energy is really different, like this one, if negative 5.48, and then the second one is negative 7, or the second one is negative negative 4, is no, you just proceed with using the lowest one. You know what I mean? You know what I want to mention about it? If you have the result, the binding energy of model 1 and model 2 is not really different, but the model 2 show a more good interactions, you can choose model 2 as your ligand receptor interaction for your publication or for your thesis. Okay. And then if you forgot what is your configuration of your docking, you can also, wait, I need to open this folder. Okay. You can also retrieve back the docking configuration, the parameter, by opening this one, the one that have conf, CONF. This means configuration file in text box. I click this one. Okay, we can see here. The center is what? Negative, this one. The center and the size and the energy range, like 2 kilocalorie per mole, exoticness 8, number of mode 10. This one you can use in your publication, like the coordinates of center, the grid size, and this one, the energy range, the exotic, and number of modes, 10 modes. Okay, up to this one, is it okay? Doctor, you have here? Are you here?
Yeah.
Yes, yes, I'm here. Don't worry. So I
I need
just
that.
want to add a few things about the bending energy. So if you remember during the first year, okay, anybody who was studying in USM and in first year, chapter 3, you will learn about the interactions, okay? So they have two types of interaction here. The first one is ionic, which is the strongest one. And the second one is a covalence. In covalence, okay, they have three types of interactions. The first one is van der Waals, okay, or London-London force. So the second one is dipole-dipole interactions. And the last one is the hydrogen bondings. Okay, among these three interactions, hydrogen bonding is the most strongest one. So to make sure your compound have a highest binding energies at a good lower good interactions, okay, you have to use at least one or two hydrogen bonding, and to show that you have a good binding between your ligand, which is your compounds, and also your receptors. Okay, the covalent is the dipole-dipole and London's is not really strong because they have just give and take, something like that. Okay, but meanwhile, for the hydrogens is a kind of it's not a real bond, but it's kind of like interactions between receptor and also the ligands between FON, between FON. So nitrogens, oxygens, and also fluorines. Okay, please take note about this one. Okay, try to remember again what you have learned during the undergraduates. Okay, this is very important because this is the basic one. Okay, this is the thing that I want to add. Thank you, Solehin.
Okay. I think that's all, Doctor, for the docking session.
That's all. Okay.
That's all. For another which is validation and blind docking whatsoever, I need to prepare another session because it's quite hard to explain it here. I need to face to face that things. But for the docking, I think I've covered the required one for publication.
Okay. So okay, maybe I can share my thought a few things about this docking. Okay, so in dockings, what you have to do is we study the interactions between your compounds and also which is your ligands with your receptors. We are doing selective, okay, because we prefer to use the potent one with comparison of the standard drugs. So beware about this one. We are not doing docking for the all compounds. No. Okay. So the second one is in terms of the 3D or 2Ds. Okay. So we have to give and take about this one. So to make sure your abstract is no, your documents is nice enough for the people to read. In my opinions, as the reviewers, it's better to show in 3D conformations, okay? Because you can see the orientations between your receptor and your ligands. For another purpose, okay, for the 2D interactions, you can put inside your supporting information. This is what we do, okay? So please make sure, sometimes they have come up with the interactions. For conventional hydrogen bonding, for example, make sure you understand pi-pi stack, pi-pi interactions. Make sure you know what is that, okay? Because as a examiner reviewers, we want to see whether your understanding about these basic interactions, okay? Okay, I just share. I'm doing some work with Ibrahim papers now. So this is my comment. I will share Ibrahim papers. Okay. So okay. So for this one, okay, my comment about this one, see, is if we go and see the figure of, okay, so for this one, okay, for my opinions, in my opinions, I'm not really like this kind of structures, because you know, if during the session with Solihins, they have types of the color of red, blue, or something like that. This one is more to the black and also yellow, greens. This is not. I don't want to say not really good, but it's not really interesting to see. And after that, they have a length between this one. We can remove this one by using this one. So if you see this one, number 4 here, it's quite messy. So please be careful. Okay, this one is quite small in terms of size. So this is very messy. So try to show that you have a very good orientations of your compounds, and try to capture that positions for this one and for this one. I didn't know what to do now, so I don't have the raw data with me, so I cannot do anything. So maybe probably I will give back to Ibrahim to do some to do it again. So please be careful what you want to read. Okay, so it's not your style when you try to write a paper is represent on yourself. Okay, very small mistakes try to avoid in terms of grammars, wordings, which one is should be italic on this one. So no need to in hurry when you try to write a papers, because it will jeopardize the quality. So I'm really happy for today's sessions, and hopefully everybody can learn something from Solehin. I would like to say thank you very much, Solehin, about this one. So make sure you keep practicing about this one. Okay, don't be shy to ask. We can learn from each other. I'm still learning, because with Dr. Tashrik, he helped me a lot about this one. Okay, so please, don't be shy to ask. Okay, so if I have this kind of attitude, you cannot go away, go far, go forwards, moving forwards. Okay, you still stay in the cocoon, which is not really good in science, because science is progressive. It's depend on yourself whether you want to move forwards and stagnance. Okay, so I wish you good luck today. Thank you very much again, and okay, and hopefully you can learn something for us. I will stop the sharings.